Hi everybody, we are Team 1053. My name is Alexander Carney, and I'm joined by Grant Summermatter and Vinny Houh, and we are tackling problem B, throw the bike or throw the race.
Here's the overview of our presentation. You see we start with going over the problem in general, talking about our major assumptions, and then going into our two cases with our trade-offs where we're not pedaling at all, and the payoffs where we actually execute the bike throw. Then we're going into solutions and simulations for these equations of motion, and then talking about limitations of our model. Here's the overview of our problem. We have this photo finish from the race between Ruth Winder and Follering, and we see that Ruth Winder just narrowly wins by executing the bike throw.
So really quickly, just to explain what a bike throw actually is, at the end of a race, competitors are sprinting at their maximum speed. Right before the finish line, the biker stops pedaling and extends their arms forward to gain a slight but temporary increase in velocity.
To figure out how Ruth Winder actually achieved this, we need to know a couple things about the bike throw. When should the rider stop pedaling and execute the bike throw, and what time interval do they have to work with? How much distance can be made up by doing this? And in turn, what is the best hand position for the cyclist when doing this? The major assumptions for our system are that the velocities can be superimposed, that we can analyze the trade-offs and the payoffs separately and then add them together to find the motion as a whole, that the ground will be flat, and that when we talk about riders sprinting, this is their maximum speed, it's a constant velocity, and that they're relatively close to each other at the finish line, so the bike throw will actually matter.
Okay, so first we're going to model the trade-offs of doing the bike throw, basically what you lose by executing this maneuver. When you perform a bike throw, the problem is you stop pedaling. Doing this allows drag and friction forces to slow you down. We can model this motion using Newton's second law, which states that the mass times the acceleration of the bike is equal to the sum of forces, quadratic drag and kinetic friction in this case. Solving this differential equation using separation of variables to get our velocity of time function looks like this. When the rider stops pedaling, their velocity decreases non-linearly with respect to their opponent. Additionally, if we analyze the distance that you lose from your opponent, we can take the integral of our velocity function from 0 to t to obtain an x of t function. So while the opponent continues at a constant velocity, the distance differential between you and your opponent will steadily increase over time. We choose to model this as a difference in distance between you and your opponent, and we will use this technique again later in our presentation.
So before we modeled the bike through, we decided to try it out ourselves. The main question we asked ourselves was if there was a way to determine the exact amount of velocity gained by performing the throw. During our test, we realized that if we could figure out how the rider's arms extend, along with the time that the bike throw takes, we could figure out the magnitude of our velocity pulse. As for our primary assumptions, we assume that the movement of the bike is related to the extension of the rider's arms, and that this causes a velocity impulse. Connecting this to our trade-offs, we assume that the rider starts to throw as they stop pedaling, but the biker doesn't pedal again during or after the throw. And finally, the bike throw has a non-negligible duration, so we need to account for drag and friction during the maneuver itself. Therefore, we decided to use a Gaussian impulse function to represent our bike throw, where the bike throw quickly boosts to some impulse magnitude, then returns to its original speed. The Gaussian function is nice because we can analytically find the resulting position increase using the integral of velocity. To determine the average velocity of this response, we needed a few different parameters that we named. So the first were A and B. These are the length of your arm and forearm respectively. You also have some sort of angle that before you are starting the bike throw, your arm makes it the horizontal, and that's this angle here. Then as the bike throw executes, you eventually reach your final position, and this angle here, this is theta h. We assume this to be a 20-degree angle. This angle has a lot to do with how precarious the position is. So as you can see in our equation, the lower theta h is, the larger the change in position is, and the larger the change in velocity is. But however, as theta h approaches 0, that really means you're throwing your entire body back, and you're in a pretty difficult position to maintain. So as that angle gets smaller, it gets harder to stay in that position. So that is sort of the trade-off in terms of how precariously you execute the throw. Using the parameters we described from the bike throw video, this is the equation for maximum position gained during the throw. Dividing this by the duration, which will be an assumed numerical parameter, we get the magnitude of velocity impulse. So then to recap everything that we have so our trade-offs, this is the amount of velocity and distance that you lose when you stop pedaling and start to execute the bike throw. So here is the velocity that you lose under drag and friction, and here's the corresponding position to that. These are just this velocity and position solutions to our equation of motion that we mentioned earlier. The payoffs, this is the amount of velocity and position that you gain. So velocity here is our Gaussian function, and the amount of position that you gain here from the Gaussian function.
Okay, so now that we have all of our equations of motion, let's just add them all together. So the true bike throw looks something like this. The perfect case with no friction or drag is our Gaussian impulse from before. Your opponent just maintains their velocity. But now that we add in the force of drag, we can see that once the bike throw is over, you are losing velocity over your opponent. And similarly, we can do the same thing for the positions, where we have the opponent's position versus the rider's position, with all drag forces included. But obviously, this graph is very hard to extract any information from, so we're going to do that distance differential technique that we did earlier in the presentation. So naturally, our solution involves determining when to start the bike throw. We will analyze the position difference over the opponent, as we want to have a positive difference at the finish line. Then we can determine how far before the finish line we should start the throw. And how we show that is that we graph the distance gained over your opponent versus the time since you threw the bike. And basically, you can imagine that we could move this finish line back and forth within this range to figure out when would be the best time to start the maneuver, where you would be ahead of your opponent when you reach the finish line. We also found 2 points to be specifically helpful: the time at which you fall behind your opponent again, and the time at which you are at maximum distance over your opponent. To generate our solutions, we created a MATLAB application where we can change around the initial conditions here, where we have initial conditions and important parameters, and then we can also fine-tune our numerical parameters. We chose these default values based on certain references for values that made sense in the real world. But anyway, we can calculate the effectiveness of a bike throw with different initial conditions, and I'd like to conclude by creating an example where this would exactly answer the reporter's question. How could you be losing right before the finish line, win on the finish line, and then lose right after the finish line? And with a certain initial conditions where your opponent is moving a little faster than you and a little bit ahead of you, we can see that this happens. But we can see that to execute a maneuver such as this, the time scales that you'd have to exploit are extremely small. In our default example, it's a little bit more forgiving, but still, professionals will have to exploit very small time windows to do something like this. And additionally, we provide a little summary where we answer our questions: when should the rider stop pedaling and execute a bike throw? What is the time interval that professionals need to make this effective? And how much distance can be made up? The benefits of creating an application was that we were able to test all of our parameters individually and see how each one affected our bike throws. So we found that heavier bike-rider combinations resulted in farther bike throws. Having longer arms or being taller increased effectiveness, and doing the bike throw faster, so doing that overall motion even quicker, resulted in a more effective result. Also, moving your body farther back increased effectiveness, but reduced your control over the bike. And we found that the maximum distance for a realistic bike throw was about up to 30 centimeters.
Now on to some limitations of our model. We do not assume drag increases during the bike throw. Certain parameters have singularity at specific values, and there's some strangeness when we input longer duration bike throws, but this isn't really realistic. And some future additions to our model is we could improve it to include this increase in drag associated with the bike throw. And finally, we'd like to acknowledge Professor Jeremy Wachter, the Skidmore Math Department, and MathWorks and MATLAB for help during this SCUDEM process.
We'd like to thank all of the judges reviewing our presentation, the organizers of SCUDEM for making this possible, and once again to our coach, Professor Jeremy Wachter. We hope you enjoyed our presentation.